Okay, so as we move forward, we're going to use Extrema on an interval derivative tests of sorts to figure out where the maximums and minimums are happening. So as a quick review, Extrema are minimums or maximums on an interval. They can be relative extrema or absolute extrema. So I have a little diagram here of this first function. We can see the diagram. Lots of times we won't know what the picture looks like, so we won't be able to see it. But on this first one, I'm just showing it to you. This is a relative minimum, also happens to be the absolute minimum. There is no relative maximum here because it would have to be relative to points on either side of it. So if it's an endpoint, there's no way it can be a relative extrema. But generally speaking, and particularly we're going to start looking at closed intervals, if we want to find the extrema, there are critical points we have to look at. Always the endpoints are critical points, not because they would ever be relative extrema, but they might be absolute extrema. So you always want to look at the endpoints of an interval. So this interval going from -1 to 2, we'd have a critical point at x equals -1 and a critical point at x equals 2. And then also, obviously, anytime the derivative is 0 or does not exist. If the derivative is 0, there's a potential that it would turn around. It looks here like we've got a derivative of 0, a slope of 0 right there, but it's not necessarily a minimum or a maximum. So these can occur. They don't have to occur, but they can occur where the slope is 0. The slope does not exist or at the endpoints. So on this first one, we have the function, and it's on this closed interval. So the first two critical points I just get out of the way are the critical values, -1 and 2. The other critical values are where our derivative, so it's just a simple power rule, 12x cubed minus 12x squared, where this is 0 or undefined. Now this won't ever be undefined, but it will equal 0, and you figure out when by factoring out a 12x squared, and you get an x minus 1. So at x equals 0 or at x equals 1, you may or may not have a relative or absolute extrema. So x equals 0, x equals 1. So you want to check all those points. So -1 comma, you just would plug it in, and you'd get 3 plus 4 is 7. If you plug in 2, you're going to get 2 to the 4th power, which is 16. 16 times 3 is 48. Just do a little scratch work over here. 48 minus 2 cubed is 8. 8 times 4 is 32, so that would be 16. Obviously, these y's are off. Sorry about that. X is 0, would give you 0, 0. And x at 1 would give you 3 minus 4, -1. So these are the critical points. Now, which ones are actually the maxes and mins? So that's where you look at the y-coordinate. So this is obviously the absolute max. This is obviously the absolute minimum. All right, so again, as far as relative are concerned, your endpoints are never going to be relative ones, so we don't need to worry about those. But if we wanted to see if 0, 0 was a relative minimum, we would need to be sure that prior to it, it's either increasing or decreasing, and then on the other side, it would have to be doing the opposite. So for example, in this 0, 0, it is decreasing coming into it, but it's also decreasing coming out of it, so it hasn't turned around. If you actually just evaluated your derivative right before 0, so at a slightly negative number, you'd get a positive times a negative. So you would know that it's a negative slope prior. And then just after, like at point 1, you'd still get a positive times a negative. So you know it's decreasing with a negative slope coming in and decreasing with a negative slope coming out. So that could not be a relative minimum for that reason. Surrounding 1, if you plugged in like a number right before 1, like 0.9, you'd get a positive times a negative, so it's decreasing. The slope is negative coming in. And if you plug in something slightly on the right to figure out what the graph is doing to the right of 1, you're going to get a positive times a positive, which is a positive. So it's decreasing or increasing coming out. decreasing coming in, increasing coming out, does tell you that that's a, oops, we're checking the 1, that also tells you that it's a relative minimum. So the next exercise, the type of instructions that you'll see as you do your homework, is to find the value of the derivative, if it exists, at each indicated extremum. So this is the indicated extremum, so we're going to find the value of the derivative at negative 2/3. So we're just going to find our derivative, and you can use the shortcut method if it allows for it. So that would be a product rule. I'm going to rewrite this as negative 3x as my first, and x plus 1 to the 1/2 power as my second. So first times derivative of the second, so the 1/2 would come out in front of the x plus 1, which we would drop to a negative 1/2, times the derivative of what's inside would just be times a 1, so I don't need that, plus the second times the derivative of the first, which would just be negative 3. So if I'm simplifying first this piece, I have negative 3x on top over the 2 and then root x plus 1 on the bottom, plus negative 3 root x plus 1. And because this is just to evaluate, we don't need to simplify, we can just plug in negative 2/3. So negative 3 times negative 2/3 is negative 3 times negative 2/3. Your 3's will cancel, your negatives will cancel, is just 2 over 2 root, and then negative 2/3 plus 1 is negative 2/3 plus 3/3 is 1/3, plus negative 3 root, and again negative 2/3 plus 3/3 is 1/3. So we have, this was just a 2. I'm going to move over here. It was 2 over 2, so 1 over the square root of 1/3 plus negative 3 root 1/3. So I will maybe rationalize so I can combine these. Multiply by root 1/3 over root 1/3. This will give me root 1/3 over 1/3 minus 3 root 1/3. So this is technically a 1 coefficient. 1 divided by 1/3 is 3. So it's 3 root 1/3 minus 3 root 1/3, which is 0, which is what the derivative should or can be at a relative maximum. And you can see obviously that has a slope of 0 there, so that makes sense. Okay. On the second one, if we want to evaluate the derivative at 0, 4 here, and we want to go and try to find f prime of x, we actually don't have any shortcuts for absolute value type functions. The only way we can find the derivative at a certain value for a derivative type function is to use the alternate form of the derivative. So the derivative, or the slope at some c value, is always equal to the limit as x approaches c for f of x minus f of c all over x minus c. So here we're looking for the slope at a c value of 0. So f prime of 0 equals the limit as x approaches 0 of our f of x is 4 minus absolute value of x minus, I'll do this, f of c, which is plugging in a 0. If I plug in a 0 here, I'm just going to have 4 minus 0, which is 4, all over x minus my c value of 0. So when we simplify this up so that we can take the limit, up top the 4 minus the 4 will cancel. We'll have the negative absolute value of x over x. Now we know from jump functions that that limit does not exist. So f prime at 0 does not exist, which we know when we look at the graph that that should make sense. Again, just kind of showing that does not exist as a slope can be grounds for a relative maximum as well. Okay, so if we flip to the back, critical numbers, this is actually easier than what we've done so far because critical numbers are just the x values where the derivative is 0 or does not exist, or endpoints, of course, if it's a closed interval. So we just need to find the x values. Those are the critical numbers, and then we're done. We don't have to find all the points here. So the critical numbers are going to come from any endpoints. Now this is this function isn't limited on a certain domain, so we don't have any endpoints to worry about. We just have to know where the derivative equals 0 or is undefined. So I'm going to find the derivative using the quotient rule. Bottom times derivative of the top minus top times derivative of the bottom, all over bottom squared. It's wise to clean up here, so you're going to get 4x squared plus 4 minus 8x squared, which is negative 4x squared plus 4. Now up top I can factor out a negative 4, and I get x squared minus 1. Okay, so this numerator will equal 0, so the slope will equal 0 if x is plus or minus 1. So those are critical numbers. And the denominator will equal 0 never, because nothing squared will give me negative 1. So I'll never achieve negative 1 plus 1 equaling 0. So these are our only two critical numbers. On our next interval, which is obviously more trig, we do have endpoints. So immediately those are critical numbers. Although actually, now that I take a closer look, those are not actually included. They just want us in between 0 and 2 pi, so not even including 0 and 2 pi. So we don't have any true endpoints because the different ends of this function, whatever it may look like, will be open circles. So we just need to find the derivative. Derivative of secant is secant tan, plus the derivative of tangent is secant squared. Now, a couple things here. There are certain places where the overall original function is not even defined. So if the function's not defined, it certainly can't be a critical point. So that's going to take out things like pi over 2. That will not be a critical point. So pi over 2 would not be allowed. 3 pi over 2 would not be allowed because tangent is undefined. And since secant is 1 over cosine, anywhere where cosine is 0 is also out of the running to be a critical point. So the cosine of 0, which isn't included anyway, well, no, the cosine of 0 is 1. I'm sorry. The cosine of pi over 2 is 0, which that's already excluded. And the cosine of 3 pi over 2. So those cannot be critical values because they're not even on the function. From here, we would just find out where does this equal 0. So I am going to factor out a secant. I'd be left with 2 tan theta plus secant. And so secant theta equals 0. Never. That's 1 over cosine theta equaling 0. That never happens. 2 tangent of theta plus secant of theta equals 0. And this is going to take some more thought. So in this particular solving, what's nice about tangent and secant is that tangent is sine over cosine, and secant is 1 over cosine. So these already have a common denominator. So you can just combine them. 2 sine of theta plus 1 over cosine theta equals 0. The only place a fraction is going to equal 0 is if the numerator equals 0. So sine of theta would have to equal, if you subtract 1 and then divide by 2, sine of theta is going to have to equal negative 1/2. So that obviously happens with a reference angle of pi over 6, but all students take calculus tells us it has to be in the 3rd or 4th quadrant in order to be negative. So if this is 6 pi over 6, we want a 7 pi over 6 is a critical point, and 11 pi over 6 is a critical point. And that's it for critical numbers, I should say, not critical points. All right, and on the last section here, locate the absolute extrema. So not asking for relative max or min, it's just the absolute extrema of the function on the closed interval. So your critical points, again, are endpoints, and any place where the derivative equals 0 or is undefined. This is never going to be undefined, but it will equal 0. If I add 12 over and divide by 3, that'll be x squared equals 4, so that's at x equals positive 2 or negative 2. And then you're just going to find the y coordinates that go along with each of these. So this one is 0, 0. This one is 4 cubed is 64, minus 12 times 4 is 48, so 64 minus 48 is 16. 2, when I plug it in, is going to be 8 minus 24, so negative 16. And negative 2, when I plug it in, is going to be negative 8 plus 24, which will be positive 16. So we have two absolute maximums. And this one here is an absolute minimum. Alright, so on the next one we do have endpoints again, so 3, comma, we can get that right out of the way. 3 over 3 minus 2 is 3 over 1 is 3. 5, comma, 5 over 5 minus 2 is 3, so 5/3. That takes care of our endpoints. As far as our derivative is concerned, we need a quotient, so bottom times derivative of the top is 1, minus the top times the derivative of the bottom is 1, all over bottom squared. So t minus t up top is going to cancel, so we're going to get negative 2 over t minus 2 squared. So when will this equal 0? Never, because the numerator will never equal 0. When will it be undefined? When t is 2. 2, however, when you go back and look at that critical value, if you plug it in, 2 minus 2, and the denominator gives you an undefined anyway. So that's not even a point on the function. So, very simply, this is the minimum. 5/3 is only 1.6 repeating, and this is the maximum. Another trig one here, endpoints. Maybe you want to do this so you can think about your values. Negative pi over 6. That is a fourth quadrant angle. We're taking the cosine of pi over 6, so that's root 3 over 2. And then we're reciprocating it. So rather than root 3 over 2, we're going to go 2 over root 3. Now, all students take calculus. Because that's in the fourth quadrant where cosine is positive anyway, that'll be positive and the whole thing will be positive. The other endpoint, pi over 3, is a 60-degree reference angle, first quadrant, so the cosine of 60 is 1/2, so the reciprocal of that to take the secant is 2. And then we need to derive, so g prime of x equals secant x tan x. So this will equal 0. Remember, we're only in between negative pi over 6 and pi over 3. So secant will never equal 0 because it's 1 over cosine. The tangent will equal 0 at 0, which I can evaluate. The secant of 0 is 1 over the cosine of 0, so 1 over 1 is 1. And tangent will equal 0. That's the only spot in that. It's a pretty tight interval from negative pi over 6 to pi over 3. So the only time that'll equal 0 is at 0. And tangent would be undefined, but not until negative pi over 2, which we never get to, and not until positive pi over 2. So those are our only 3 points. And of them, 2 divided by root 3 is 1 point something. So this is your max and this is your min. And then lastly, our interval again. So we have a critical point at -1 something and 3 something. I think this one we definitely need a calculator for if we're taking the cosine of -1. So -1 squared is 1 minus 2 minus the cosine of -1. And I'm going to bet we need to be in radians, okay? So that gives me -1.5. If I plug in 3, I'm going to get 9 minus 2, which is 7. 7 minus the cosine of 3 is 7.99. And then the derivative of this, y prime equals 2x minus the derivative of cosine is negative sine. So 2x plus sine x, and we got to think about when this would ever equal 0, and this is definitely a thought type question. It will never be undefined, but when will it equal 0? Okay, so just logically thinking, the only way that this plus this is going to equal 0 is if they're opposites of each other. So if this was a positive something, this would have to be the negative version of that. That's actually not going to happen, because if you plug in 3, for example, that's obviously 6, so positive, and the sine of 3, given that this is radians, and there's 3.14 radians, all students, even if you plug in 3 radians, the sign is still going to be positive. So you'd have a positive plus a positive, which is obviously not 0. And if you plugged in a -1, so something down here, that's going to be a negative number, plus your sign of that is going to be a negative number, so you're just accumulating negatives. The only way this can actually equal 0 is if x equals 0, because 0 plus 0 is 0. So just, unfortunately, there's no, like, work that can be shown for that. You just have to think of that. And so, you know, 0 is obviously always a special case worth testing, but x equals 0 would make that work as well. So if you plug in 0, you're going to get 0 minus 2, which is -2. The cosine of 0 is 1, so you'd have -2 minus 1, which would be -3. So with that, we have a minimum and we have a maximum. And I went ahead and graphed this function specifically on the interval from -1 to 3. So -1 to 3, took a peek at it, and you can see the absolute minimum is here, so 0, -3 makes sense, and the absolute maximum is at one of the endpoints, 3 and then 7.99. So your homework is page 217, 1s, 5s, and 7s, 1 through 45.